So we've talked about a principle of impulse and momentum. Now we've talked about angular momentum. Well, we can combine those two ideas with our principle of angular impulse and momentum. So just as we had in our relationship with forces and momentum, right? That principle of impulse and momentum, we had force is going to be m dv dt, right? We said that force was essentially like the time derivative of momentum, where momentum is your m times v. Right? Your force is just the time derivative of that. And that gave us this relationship where we had mv1 plus the integral of f dt equals mv2. Right? That was our principle of impulse and momentum. By the same logic, we can actually apply this to our angular momentum and impulse as well. So for our angular momentum, it is actually our moment. Our moment we can get by taking the time derivative of angular momentum. So if we take our angular momentum, the derivative of that with respect to time, we get a moment, right? It has the same kind of time derivative relationship between the angular momentum and the moment as it does between the force and the linear momentum. So by this logic, since we know that our force is related to moment is r cross f, and our angular momentum is related to linear momentum by r cross mv, we can create this relationship with our moments and angular momentum, and this gives us our principle of angular impulse and momentum. So our big equation here that we're going to use is our initial angular momentum plus the sum of all of those different moments. All of those moments integrated with respect to time equals our final angular momentum. Where initially you have your angular momentums, and then this center term, this is the angular impulse. And then, of course, we already know those. H's as angular momentum. So this equation here, this is a very handy equation for curvilinear motion, right? Before we were working with just linear momentums, we were working in linear systems, but anytime we're doing curvilinear motion, right, having motion along some kind of curve, curvilinear motion, we're going to want to use our principle of angular impulse and momentum. Curvilinear motion is what I meant to write here. I was going to write momentum again. Curvilinear motion. That's when you want to use this. And you can use these in combination. You can use your principle of linear impulse and momentum with your principle of angular impulse and momentum. You can use these together very similarly to statics, where in statics we had our sum of x forces is 0, sum of y forces is 0, sum of moments equals 0. This is also something that we can do with our impulse and momentum here in dynamics, right? We can treat these linear ones as like our x and y components and use this moment relationship as the moment relationship, right? Use those moments to use this principle of angular impulse and momentum for any rotations. So we'll take a look at a couple of examples of how we can use this equation, how we can apply it when we have some curvilinear motion systems. In this first example, we've got a 2 kilogram sphere that's attached to the end of a rod which rotates in the horizontal plane centered at O. If the system is subjected to a moment of m equals, and I just realized my squared got dropped there, m equals 0.9 t squared, which we also do see over here in the image, 0.9 t squared, where t's in seconds, determine the speed of the sphere at the instant t equals 5 seconds starting from rest. So again, a really good indication that we want to use our angular momentum is that we've got velocities, we've got a moment, and it's curvilinear motion, right? Going in that rotation around point O. So since we've got a good candidate here for our principle of angular momentum and impulse, angular impulse and momentum, I'm going to go ahead and write that out. Write out our initial angular momentum plus the summation of any applied moments from t1 to t2 m dt equals our final angular momentum. So those angular momentums, since we're kind of working in a scalar system here, this isn't like a 3D system we're really looking at, we can look at it kind of as the horizontal plane, like as the plane that we're kind of looking at here. R mv, right, R cross mv plus the integral of that moment, only the one single moment is being applied, we don't actually need that summation, is going to be our final R times m times velocity. So let's see what kind of information I can pull from my problem here. I know that my mass is 2 kilograms. I've got a moment in terms of time, 0.9 t squared. And then this arm here is giving me my radial distance to the particle, right? From O to the particle is always going to be 0.6 meters, since it's fixed there on the end. So my R is going to be 0.6 meters, and then I know my time is going from 0 to 5 seconds. And to determine the speed of the sphere at t equals 5 seconds starting from rest. So that tells me that my initial velocity is 0. We're going to neglect the mass of the rod. So we're just looking at that particle there at the end, that 2 kilogram sphere acting as a particle. And we can start plugging stuff into our equation. So we've got R, which is 0.6 times the mass of 2 kilograms times the initial velocity. Whoops, that's 0. I guess I really didn't need any of that other stuff, but that's okay. It's in there anyways. Plus my integral from 0 to 5, right? Going from 0 to 5 seconds for our moment, 0.9 t squared dt equals our final angular momentum, which is 0.6 times the mass of 2 kilograms times the final velocity. And that's what we're trying to find, right? We're trying to find that final velocity. So this term goes to 0. I can go ahead and do this integral. 0.9 t cubed over 3, evaluated from 0 to 5, equals 1.2 times v2. And then as I solve for v2, I can plug my 5 in here. 0.9 times 5 cubed over 3. 0 term goes away. I get 1.2 v2. Actually, I could just move that over here. I might do that. Divide out that 1.2. And when I punch this guy into my calculator, I'll get my final velocity of this sphere is 31.2 meters per second. That's the final speed from this applied moment that is increasing significantly with time, right? With time squared, moment increases significantly with time. So it ends up starting from rest 5 seconds later, it is going at 31.2 meters per second. And of course, that velocity, this is curvilinear motion, but we know that velocity is always going to be tangent to our direction of motion. So we know which way this v is going. There's no need to give a direction for this velocity. is just going to be perpendicular to the arm of this rotating sphere here. Let's go ahead and take a look at one more example. All right, so in this example, we've got a 1.5 megagram car traveling along a circular road as shown. The traction force of the wheels is F equals 150 t squared newtons. Determine the speed of the car when t equals 5 seconds. Car initially travels with a speed of 5 meters per second. Neglect the size of the car. So if we kind of think about what we've got going on here, it's clear we have curvilinear motion. This car is moving along this road that has a radius of 100 meters. But we're going to need to kind of decide what forces are going to contribute and how we're going to put this together with our angular momentum. So our angular momentum equation, again, we'll write this principle of angular impulse and momentum. That's our initial angular momentum plus the summation of any contributing moments dt. And that gives us our final angular momentum. So here we're given a force, right? We're not given a direct moment like we were in the last one. It says that our force equals 150 t squared. Now, of course, we know our relationship between a moment and a force. We know that a moment is going to be r cross f. And we know what that r is. We know what that distance is. We're trying to find this really about the center of this circle here. Right? It's going around this curved road. If we kind of rotate our thumb going in the direction of that dot, that car is rotating around the road. It has an angular momentum. It has a moment there from that force F. And that's really the only force that's going to be contributing to our angular momentum here. Like that's going to contribute to this impulse portion. Because if we look at this from our top view, it's pretty clear that's the only force we see. This is our traction. Right? It doesn't indicate that it's like moving up and down the hill at all. It doesn't indicate, any side-to-side movements or forces. Now, of course, we do know if we were to look at like a front view, for example, instead of the top view. So here's the window. There's a man in the car. Here's the headlights. The car is driving at you. If we had a free body diagram for this, we know, of course, it has a weight and a normal force on this. But of course, these aren't any forces that cause a moment, right? They run perpendicular, they run parallel to our axis that we're taking a moment about, right? This center of this circle here. Those forces run parallel to this axis in the center. So we don't have to worry about these forces. They're not causing any moment about this center point. The only force that's causing any moment about that center point is this F force. F is 150 t squared newtons. So with that in mind, we can go ahead and move on and kind of break down our angular momentum here. We've got r times m times v, right? So that distance away from our origin times mass times velocity 1, plus there's only one force contributing at all to our moment. So we're going to have the integral from t1 to t2, r times f dt equals our final angular momentum, rmv2. Then I'm going to go ahead and start plugging some things in, see how far I can get with the information that I have. So the information that I have, and usually I write it out first. I don't know why in both of these problems I just haven't even thought to write it out till we get here, but I've got a mass of 1.5 megagrams, which a megagram is 1,000 kilograms. So 1,500 kilograms. F, they told us, is 150 t squared. We want to find the speed of the car in 5 seconds. And the initial speed, v1, is 5 meters per second. Let's plug some stuff in here. My R is given in the image, 100 meters times the mass of 1,500 kilograms times our initial velocity is 5, plus the integral from 0 to 5 of 100 times F, 150 t squared dt, equals R is 100 times the mass of 1,500 times V2, which is what we're trying to find. I'm going to punch those things into my calculator, and I'm going to get 750,000 plus, if I take this guy, 100 times 150, that's 15000 t cubed over 3 from 0 to 5 equals 150,000 times V2. And so I can evaluate that integral, and that's going to give me, the integral gives me 625,000. So if I add those together and divide out that 150,000, 1,375,000 over 150,000 is my V2. So my final speed of my car after 5 seconds is 9.17 meters per second. All right, so this principle of angular velocity and momentum, not angular velocity, principle of angular impulse and momentum is really useful for these curvilinear problems where you've got forces or moments where you're trying to find this velocity. It can kind of shortcut you and save you some time in these problems using this principle of angular impulse and momentum.